Assalamualaikum and a very good morning to Dr. Amalullah. My name is Nu'ain Najah. My metric number is 29389. This is my group member, which is Nur Umairah, Siti Umaisarah, Hikmah binti Nordin, and Sami binti Hassan. So, our group choose the problem which is assignment problem, and the two design techniques that we choose, which is branch and bounce and exhaustive search. So, I will explain what is assignment problem. The assignment problem is a fundamental combinatorial optimization problem. It involves finding the most cost-effective way to assign a set of tasks to a set of agents, where each task must be assigned to exactly one agent and each agent is assigned exactly one task. The goal is to minimize the total cost of the assignment, and this problem can be represented as a bipartite graph. The problem also is a fundamental optimization problem that arises in a wide range of real-world scenarios, from workforce management to logistics and scheduling. At its core, the assignment problem involves assigning a number of workers or resources to an equal number of tasks or jobs in the most optimal way, typically to minimize the total cost or maximize the total profit. So this is one of the technique that we choose, which is exhaustive search. So exhaustive search, also known as a brute force search, this approach to problem solving is characterized by its systematic and comprehensive exploration of all possible solutions, ensuring that no potential answer is left unexamined. While this method may seem straightforward, it holds a significant place in the arsenal of algorithm strategies, offering a reliable and guaranteed solution for certain types of problems. The algorithm generates and checks each potential solution, ensuring that no viable option is overlooked. This meticulous approach is particularly useful when the search space is well defined and manageable, as it provides a surefire way to find a solution if one exists. So what is branch and bounce? The branch and bound method is a powerful algorithmic approach used to solve a wide range of discrete and combinatorial optimization problems. At its core, the branch and bound technique is a systematic way of exploring the solution space of a problem while intelligently pruning away parts of the search space that are unlikely to contain the optimal solution. The fundamental idea behind the branch and bound method is to divide the original problem into smaller, more manageable sub-problems, and then to evaluate the potential of each sub-problem in terms of its ability to lead the optimal solution. This is done through a process of branching and bounding. So why we choose exhaustive search? First, guarantee optimal solution. Exhaustive search consider all possible assignment of tasks to workers, ensuring that the optimal solution is found. This is because the technique systematically enumerates and evaluates every possible assignment, allowing it to identify the assignment with the minimum total cost or maximum total benefit. Second is the exhaustive search is suitable for small-scale problems. For assignment problem with a relative small problem or task and workers, the search space is manageable, making exhaustive search a variable and practical approach. As the problem size increases, the number of possible assignments grows exponentially, making exhaustive search computationally expensive and impractical. And why we choose branch and bounce? First, guarantee optimal solution. The branch and bound technique systematically explores the solution space by generating and evaluating all possible assignments. By maintaining a lower bound on the optimal solution cost and pruning branches that cannot lead to a better solution, the branch and bound method is guaranteed to find the optimal solution. Second, efficient exploration of the solution space. The branch and bounce approach intelligently explores the solution space by prioritizing the most promising assignment based on the lower bound calculations. This allows the algorithm to quickly converge to the optimal solution, making it more efficient than a brute force exhaustive search.
Assalamualaikum. My name is Numara binti Syamsul. Metric number 292355. I will continue the demonstration assignment problem using assertive search algorithm technique. The assignment problem involves finding the optimal way to assign people to n jobs such as the total cost is minimized. Each person can be assigned to only one job and each job can be assigned to only one person. The cost of assigning person I to job J is given by Cij. In the example provided, there are 3 people and 3 jobs, which the cost matrix C as follows. The assertive search method involves checking all possible permutation of assignments and calculating the total cost for each permutation. There are n factorial permutation to check. Okay, the first step is we need to list all possible permutations of the assignments. For 3 people and 3 jobs, there are 3 factorial, which is 6 permutations. We get the person 1 job 1, person 2 job 2, person 3 job 3, person 1 job 1, person 3 job 2, person 2 job 3, and we list until we get the person 1 job 3. For the next step, we need to calculate the total cost for each permutation. For the first permutation, we get the person 1 job 1 plus person 2 job 2 plus person 3 job 3, which is 9 plus 4 plus 1 equal to 14. For the next permutation, we get the person 1 job 1, person 3 job 2 plus person 2 job 3, which is 9 plus 8 plus 3 equal to 20 until the last permutation, which is person 3 job 1 plus person 2 job 2 plus person 1 job 3, which is 5 plus 4 plus 7 equal to 16. The last step, we need to choose the permutation with the minimum total cost. In this case, the permutation person 2 job 1, person 1 job 2, and person 3 job 3 has the minimum total cost, which is 9. Thus, the optimal assignment is person 1 assigned to job 2, person 2 assigned to job 1, and person 3 assigned to job 3.
Assalamualaikum, my name is Sabi binti Hassan. My matric number 292802. So I'm going to explain about branch and bound technique algorithm. So let's go through step by step to get the optimal solution. So we go to step 1, which is problem definition. There are n people who need to be assigned to n jobs, one person per job. The cost of assigning person I to job J is C matrix IJ. Find an assignment that minimize the total cost. So we have job 1, job 2, job 3, person 1, person 2, person 3. So let's go through next step. Step 4, further branching node level 2. We add 2 branch to level 1 node. Node level 2, we assign left job to person 2. What it means here is from the first level node, we have P1 to job 1. So in level 2, we assign person 2 to job 2 and job 3, which is not done yet in level 1. So then we calculate the cost of level 1, which is 9, will add it with cost of level 2, which is 4, make it total of the cost of the solution for this level, which is 13. The same way goes to all the node solutions. Step 4, further branching node level 2. We add 2 branch to level 1 node. Node level 2, we assign left job to person 2. What it means here is from the first level node, we have P1 to job 1. So in level 2, we assign person 2 to job 2 and job 3, which is not done yet in level 1. So then we calculate the cost of level 1, which is 9, will add it with cost of level 2, which is 4, make it total of the cost of the solution for this level, which is 13. The same way goes to all the node solutions. Next, for step 5, we have further branching node level 3. So in here, we add another branch to level 2 node. which is basically the job that left for each solution. So how we are going to see the solution is from the level 1 node, then we go to the next branch and this at level 3 branch. So that is one solution. So it goes to the same way to the other nodes as well. So we have here 6 proposed solutions. So now when we assign, after we assign the person 3 with job left, then we are going to calculate the cost of the solution. So from the cost of solution at level 2, which is 13, now we are going to add with the cost of solution of level 3 of P3 to job 3, which is 1, make it the total cost for this solution is 14. So the same way goes to the another solution also. So we have P3 to job 2, the cost of solution is 20, P3 to job 3 is 9, P3 to J1 is 10, P3 to J2 is 21, and P3 to J1 is 16. So that is the total cost of each proposed solution. So next we go to step 6, which is optimal solution. The optimal assignment is found by choosing the path with the minimum cost. So in here, we found that P1 to J2, P2 to J1, and P3 to J3 is giving the minimum total cost. So the total cost for this solution is 9. So in here, we found that is the optimal solutions for this whole problem. So the last step is step 7, which is result. So the optimal assignment with the minimum cost of 9 is P1 to J2 cost 2, P2 to J1 cost 6, P3 to J3 cost 1. So make it the total cost of this solution is 2 plus 6 plus 1, which is 9. So that's how we solve the problem using branch and bound technique algorithm. Thank you.
Assalamualaikum, my name is Siti Nurmaisara binti Nursyam. My metric number is 293541 and I will explain about running time analysis. For the first one is exhaustive search. For an exhaustive search, the time complexity is O of n factorial, where n is the number of the cities. The fact that there are n factorial, the potential permutation of n cities lead to the factorial time complexity. Take a situation with 5 cities as an example. There are 5 factorial equal to 120 alternative paths in this scenario. The number of permutation increases rapidly as n increases. For example, there are 10 factorial equal to 3,628,800 potential roads with 10 cities, and 20 cities increases that number to 20 factorial equal to 2.43 times 10 to the power of 18. For larger value of n, exhaustive search is not feasible due to this exponential growth rate. O of n is the space complexity of exhaustive search. The current permutation of the city and the tour distance must be stored in this area. It may also be necessary to use some additional data structure, such as list or array, to keep track of city and their respective distance. However, the main issue with exhaustive search is not its space complexity, but its extremely high time complexity. Next is branch and bound. The worst case time complexity of branch and bound is also O of n factorial. Since in the worst case scenario, it may need to analyze every possible permutation. But in practice, branch and bounds usually happen faster because the pruning method works better. Initial lower bounds on tour length and starting city are entered in the algorithm. The cost of partial tour is then determined after it recursively analyzes each branch or possible next city to visit. A branch is pruned or left unexplored if the partial cost plus an optimist estimate of the remaining visit exceed the best known solution so far. The ability of bound so effectively reduce the search space and has a significant impact on real-time complexity in practice. Branch and bound has O of n space complexity, mostly due to the order of priority queue used to store intermediate states while the search is in progress. Since the algorithm examines multiple branches, this space is needed to keep track of cities and their distance. The real benefit of branch and bound, despite having a space complexity comparable to exhaustive search, is that it improves time efficiency through efficient.
Lastly, now let's look at the comparison efficiency for both exhaustive search and branch and bound. First, let's look at the time complexity. First, for exhaustive search, the time complexity is the O in bracket of n multiplied by n exclamation mark, which indicates it grows factorially with the size of the input, making it impractical for large datasets. The branch and bound, on the other hand, has a best case time complexity of O in bracket of n the power of n the power of 2 multiplied by 2 the power of n, and a worst case complexity of O in bracket of n exclamation mark. This means that although still exponential, it can be more efficient than exhaustive search in certain cases due to its pruning techniques. Next, we move to the space complexity. Exhaustive search has a space complexity of O the power of O in bracket of n, which means it uses a linear amount of memory relative to the input size. Branch and bound has a base case complexity of O in bracket of n multiplied by 2 the power of n, and a worst case complexity of O in bracket of n exclamation mark. This shows that it can potentially use a significant amount of memory, especially in the worst case. Okay, finally, in terms of suitability, exhaustive search is suitable for tiny problems due to its simplicity and straightforward approach, while branch and bound is more suitable for moderate to large problem sizes because of its ability to reduce the search space effectively, making it a better choice for more complex problems. So the conclusion of this, we can conclude that while exhaustive search is only practical for very small instances of TSP problem, TSP, branch and bound, offers a more efficient and scalable solution for moderate to large instances. Depending on the problem size, branch and bound is generally the better choices for solving TSP in most real-world scenarios. That's all from us. Thank you.